Okay, so anyway, so I have a new setup actually. New camera, new microphone. It's just my phone I connected to the computer, which was free and done after I acquired a camera specifically for that purpose. So I feel a little bit dumb. And my computer is a little bit noisy. If you are too noisy, computer, I'll have to silence you and you will not like it. But since it keeps making noise even while I talk, I guess it's normal since we are recording, but like, yeah, I don't know. Anyway, the more spike for your computer. Let's just check that it's not bugged with those settings. Everything's running easily. Yeah, it's not that complicated. It's the whole setup. Okay, anyway. So let's study a bit. It's quite early today, a bit earlier than previously. So let's take advantage of that. And also, yes, I have nothing to learn. Almost everything is in my mind from previous times. So today, what we will try to do, honestly, it would be good if I like review this one, and learn this whole one, and maybe even add some new sources because we have new material to learn. Yippee! Anyway, this can go down. This can go down. This can go. Can I do that? I don't know. He's bugged. Just leave that guy alone, I guess. I hope, yeah, okay. He did not bother anything else. Okay, so let's just run some timer here. And let's just get learning, I guess. So this is good. Okay, so for stable DC GANs, you use batch normalization in all layers of all networks. Training is formulated as a minimax game with the objective function. Oh, hey, I need a solution to write mathematical formulas at some point. How could I do that? With this maybe? What's the easiest way to write mathematical formulas? Because maybe I can use like Notion, but it's a bit like overkill at some point. Do you have like bouillon somewhere? Can you just do that well? But yeah, it's a bit weird. So anyway, because it will be like very slow. The good thing is to have like a whiteboard maybe, but whiteboard is also a bit complicated, a bit tedious to use. Oh, I'm leaking the browser's images. Pretend you've seen nothing. Okay, let me check. So if I try to write this formula, it's complicated to write with a mouse. Never mind. Let's just try to get this from here. Anyway, so you minimize you want to minimize the generator, maximize the discriminator out of some experience of log of discriminator of real images plus or minus, it's infinite. Why? I don't know. Plus e of 1 minus log of discriminator of generator of z, I believe. Minimize g, maximize d, epsilon of dx plus epsilon of, okay, the 1 is inside the log. So that's, okay, it was so complicated. Let's just pretend I forgot it. So what's that? That's characteristics of non-targeted adversarial attacks. Goals. It was complicated and it was kind of a guess. So, while trailing GANs, when the mod collapse happens, all pictures, blah 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 blah, you can just compute the similarity between the fed images and the already existing images to like slap the generator if the similarity augments. Kind of. These are adversarial attacks. Algorithms for adversarial attacks. Okay, so the DC GAN. The generator is just convolutional layers that are also fractionally stride. I often forget that it's for upsampling, so let's just... Okay, so the formula I'm not looking, it's you still minimize G, maximize D of the experience of log of discriminator of a real image plus experience of log of 1 minus T of G of Z. Check. Yes, right. G wants to minimize this goal. G wants to minimize this so that this one is near 1. Oh yeah, this one I mean. Yes, okay. I need to think. Okay, let me just do something real quick. Anyway, I'm back. I'm not that motivated to learn this anymore. But we gotta do what we gotta do, right? So the generator is an upsampling network composed of fractionally stride layers, convolutional layers. And he wants to minimize all of this because if it's minimizing, this one is getting through the roof, which means that the discriminator thinks that generated images are real. So it's giving 1, and if it's giving 1, 1 minus 1 is going down, and if it's going down, that's what he wants to do. He wants it to go down. Anyway. So if you have more than 2 groups, when to do Friedman? Friedman is done when this is not parameterized, that's for sure. Let me turn off. I can do that, I think. My bad. Apparently I cannot. So interesting. What was I saying? So not parameterized, but matched. Crystal Wallis, it's when you are still not parameterized, but you are also not matched. And if you are non-parameterized but matched, that's what we saw. It's F something. I was about to say Friedman. Okay, 2 groups matched and parameterized. it's a t-test, but repeated t-test, paired t-test. That's not exactly all that. Repeated measure ANOVA when you are parameterized and matched. Data such that there exists no correspondence, so it's like it's non-matched data. Simply. Parameterized test, 3 hypotheses, it's simply independence, normality, and homoscedasticity. So homoscedasticity. So if the two groups, more than two groups, H1, you do post-hoc test. Non-parameterized but match Friedman test. More than two groups. So it's t-test, repeated t-test. Matched, paired. It was a paired t-test. More than two group. ANOVA, it's always more than two group. Post-hoc test you perform after the main test to discernate which pairs really differ from one another. Non-matched data, simply data such that there exists no relation between one data and another data in both groups. One-way ANOVA, parameterized but not matched. More than two groups. Parameterized and non-matched. One-way ANOVA. Non-parameterized, non-matched. Critical Wallis. Repeated measure ANOVA. Okay, great. This is done. This one is done. I'm mouse maxing. I'm not keyboard maxing right now. Okay, let's try this one, which is kind of hard if I remember. But everything is hard out here. So. Okay, so what? Okay. Conditional GANs. Okay. Non-supervised. I don't really remember. Okay, yes, I think I see. Discriminator. It judges if the generated image is an image of the domain E and Y, and if it is realistic. Okay, realistic is omitted, but he's checking if the image is from the correct domain. So this one is simply you have P of nothing, that's like the noise sampling, and you get xt sampled from this one, xt sampled from this. Okay, so advantages of EM for GANs. So EM is robust when you have 2 plus categories, I think, that overlaps when classes can have more than 2 groups. Can have different types. You can have like reals, integers, and stuff like that. It always converges, local or global. You get the idea. I need 2 more. Oh Lord. I think it's quite robust to outliers. And the last one, I have some ideas, but I think it was the fact that it's faster than KNN. I think it's from it's not this one. I think I mean it's supposed to be faster than KNN. Yeah, no, okay, it was this one. What is faster than KNN then? I don't know. It's been a while. Anyway, so it's classes actually, not category. Yeah, it's kind of the same. And characteristic, not classes. It's a bit complicated. Anyway, so your typical GAN algorithm. So I don't know which card is that because I have like 2 cards. I know it's a bad practice, but you int discriminator and generator on some random bullshit. It's 2L. Then you like repeat until convergence, and it's like if you fix the discriminator, you change the generator, and vice versa. Yes, that's correct. Okay, so examples, we have segmentation. So it was for, okay, for conditional GANs. So we have segmentation. It's like a day and night picture. You just can turn a day picture into a night picture. What is a prior in VAE? A prior is, so you have your encoder, which receives an images. Images is encoded into a latent space, and the vector of the latent space, that's the prior. Oh, not really. So since it's a variational autoencoder, you don't encode in the latent space a vector, you encode characteristics of a probability distribution in the latent space, which means that the encoder gives to the decoder not a prior per se, but a kind of a Gaussian, a normal distribution from which Z is a prior is sampled, a real vector, prior vector, and from which it is reconstructed, not an image, but another distribution from which you can sample an image. I had forgotten that, so let's be merciless. Anyway, so it was like 2 plus classes that overlaps, categories with different types, converges, resistant to outliers, and strong representation of categories. Great, okay. So discriminator for conditional GAN, image to label, discriminator takes the labels. And the okay, if you want. What it does is generator takes the image and outputs some labels. The discriminator takes the image and the labels generated, and he wants to guess whether the label really from the image or if they have been generated. He's like, did you made up these labels, or were they in the package? And I meant this one. What's the prior? So the prior is the vector sampled from the distribution encoded by the encoder in the latent space. Type sheet. So conditional GAN, well, it's just edge image. You go from an edge and you encode an image. The LVM. So in a VAE, so that's what we are talking about. The decoder defines the the generator model, generating model if you want. Conditional GAN, sketch to image. There are some dumb cards, some free cards in that, I acknowledge. Conditional GAN functions with matched paired data, paired as in statistically paired, not really good. So important elements to train VAE. Wow, I have no ideas of what that card might be. I think it's like quality prior, good sampling distribution, from which you prior, quality of encoder and decoder, of course. But like, what's the last one? Oh, it's like curated data. Quality of encoder, quality of prior, correctly pre-trained dataset, distribution of generation. I've learned this because it was like specifically put as such in the course, so I wanted to be able to know that if it had come up in test. That's why these cards are like very kind of specific. Discriminator judges whether the image corresponds to the sound, and if the image is realistic. Okay, sometimes I've put it, sometimes I've omitted it, but the discriminator kind of always judges if the image is realistic or not. But we did not learn how it does this. Maybe it doesn't really does it. It's like not really precise of the definition. But the thing is, it checks whether the generated images properly correspond to the input origin. Decoder. So that is what I was trying to explain earlier about the VAE. So decoder takes a prior sampled from the distribution. DLVM introduces variable latent variables, neural networks, and he's looking for something like, I hate this card. It's like oh my god. I forgot everything. I mean, the DLVM is a generative model that's looking for it's like Q of Z given X some dumbass bullshit. It's exactly the opposite. I don't understand it actually. Theta is the parameters, probability of sampling X given Z. So given the prior, you reconstruct probability of sampling the prior. That's so weird. I don't get it. Sometimes I just don't get it and never learn it because I'm lazy. Anyway, so discriminator takes an input image and domain. This is an approximation, parameterized approximation. Yes, it's like in the other sense. It's removing the noise. It's learning to remove the noise. So it's like reverse kernel, kind of. So EM, the downsides of EM. I think it's here the KNN, it's lower than the KNN. It's not faster. And it's not KNN, it's KMINS. So it's like not so far, but quite. The encoder approximates the latent prior. Posterior. I don't know why it's posterior. Yeah, it's supposed to be. Well, it's his posterior, yes, but it's his prior. Make it make sense. Okay, so DLVM, it's learning a model P theta x z equals P z P theta x knowing z. Some dumb shit. Don't question, sometimes you don't question. A diffusion model functions with two frames. Numbers of latent variables in a DLVM. One variable, latent variable is a VAE. It's the prior. Well, it's all the intermediate state that the decoder doesn't know. It's slower than Cummings. While diffusing encoder, while you are diffusing, the encoder is fixed, of course, and the decoder is learned, because encoder is just adding noise, so it's a fixed operation, and decoder is not learning to generate image, it's learning to predict the noise, and the noise he predicted, he removes, kind of. Generators plays the role of classifier. Multi-label. I need to study this again, because I forgot kind of everything about machine learning and using neural networks. I just said classifier, not multi-label, but it's kind of course. Algorithm used to estimate, well, that's the EM, expectation maximization algorithm. DLVM, deep latent variable model. Characteristics of conditional GANs. Is a diffusion model? Yes. What part of the VAE takes X? It's the encoder. You see that's a bad card because you have encoder, decoder in the picture, and in the sentence it's the same. So the brain is really making shortcuts like this. Trust me. When you see the cards like thousands of times, it's quite slow. But I'm explaining to myself also. We've seen it earlier. JMMR. You can approximate any density or distribution, yes. Data distribution, same. DLGM, deep latent generative model. GANs overperform design for classification. Multi-label, yes. That's the fact that in a GAN you have like several Gaussians, and data point is not only from one Gaussian, it's from all the Gaussians up to a certain probability. So it's like probably from this one, less from this one, it's from this one. It's a vector of probability. EM for GMNs. So we said good when there are two or more classes that overlaps. X0 is obtained when you sample the real images space. P star, of course. EM, Ricard. Encoder takes as an input an image X and produces a distribution, a Gaussian characterized by the the variance and the mean. If I'm saying some nonsense. Gaussian distribution in the latent space, of course. So you are encoding, so you are adding noise with the kernel, and so the last one is you have xt minus 1 sampled from the kernel of xt minus 2. Tac. Works when categories are of different types. Characteristics, not categories, but same. I know. A DLVM. I was hesitating between DLGM and DLVM, but a DLGM is a DLVM. XO. It's from a VAE. What model is simpler than? What's the simplest DLGM? It's the autoencoder. It learns the generative model, which is P theta of X given Z. It learns to reconstruct X when you give it a Z, and theta for the parameters that you modify. Characteristics of non-supervised GANs. Oh, it was conditional non-supervised. Okay, my bad. Image to label. Generator plays the role of a multi-label classifier. It takes as an input the image, outputs labels. Discriminator takes the image and the labels and judges if the labels correspond to the image. Simple. Each watt of a GMM, each Gaussian of a GMM is associated with a blah blah blah. Generator takes as input, we just seen it. DLVM is a generative model that introduces variable latence, use neural networks to parameterize its distribution, to train a VAE quality of the generative distribution you use. Tell outlists, there is a typo here. The GMM are universal approximate. Anyway, characteristic of conditional non-supervised GANs. Okay, in the other sense, that's the denoising kernel. You just apply this kernel with xt. Simple. Transformation is progressive. We have t intermediate steps or hidden variables, latent variables, if you prefer. GANs functions with matched datas. Generators takes the image, the paired datas, and generates something, and something happens, and I don't know. Okay, let's see how slow we are. A bit less slow. But that's a tough one. And how much we did? 61. Important elements to consider when training your your VAE, of course. DLVM, Deep Latent Variable Model. Generator takes as input a noise and an input Y. Characteristic of a conditional GAN H2 image. Well, the matched datas are edges and images, I guess. Example of tools, edge to image, pix to pix. Correct. Diffusion models learns to predict the noise. It's what I was teaching you. Okay, so that's like the mainstream definition. My bad. I forgot I have the two cards. That's the mainstream one where people think they understand diffusion. It's like, oh, it's just predicting to do what actually? It's just removing noise. That's so smart. Yes, actually it is, but the AI doesn't know about removing noise. It's just predicting the noise. And then a dumb algorithm just takes the predicted noise and subtract it from the noise, the image. Kind of. If I'm not mistaken. Actually, maybe I'm the dumb one here. Anyway. Conditional GANs match data, so you take a noise and an input. The discriminator takes the output and the signal, and it judges if the images correspond to the output, to the input. GMM, with enough Gaussians, you can approximate any data distribution. Any Gaussians well used, of course. What's the diffusion stuff? Is the diffusion rate learned? No, of course not. I mean, it can be actually, yes, it can be. Applications, seen in class, so you have black and white, Isn't it like a sketch to, or it's, I think it's from a drawing to a real architectural picture, segmentation to a realistic image, label to facade, yes, kind of. Conditional GANs. Noise to image, kind of sound to image. Scene GAN for the conditional GANs, non-supervised. Transformation is progressive. We have T variables. The BT, the diffusion rate of the kernel. VAE, of course. Conditional GANs. Discriminator takes the input and the output of generator. What's the advantage and the disadvantage of EM in the log sum loss? Man, I don't know. Let me turn on the light, maybe, because we can't see shit here. This one, I think it's almost the hardest one, because it's really like a lot of learning by heart some situations to really understand what's up. Let me just make a small break. Okay, so anyway, made a small break. Small break from all this labor. So what's the advantage and the downside of EM? I don't know. I still don't know. Easy to define, hard to optimize directly. Okay, I have no idea. Now I remember, but anyway. Matched data used, edge to image, well, an image and an edge. In the diffusion network learns to predict the noise, numbers of latent variables per models. What's the mathematical formulas, the simple mathematical formulas of the cycle GAN, total cycle GAN? Man, total cycle GAN? I think it's like, no. It's like you have your generator and your other generator and X and Y, and it's just like the loss of the generator with the domain of Y and X and Y plus the same loss for the other generator Y domain X plus the cycle loss cycle, if you want, which just takes, I think, GN. And you had a wait. So you have your first GAN loss, your second GAN loss. Okay, that's good. So EM, okay. EM is easy to understand and to define. It's hard to optimize directly because of the I think it's the integral you have to compute in high dimensional space. It's intractable, I think, because it's not observed. EM alternates between two steps: expectation, where it's saying like I think this variables is from these Gaussians, and maximization, where it uses this distribution of expectation to raise the weights of each Gaussians. Not even sure what I'm, if what I said is correct, but I'm not sure of anything. So probability to sample xt is equal to probability to sample xt from the kernel of xt minus 1. More or less. What parts of the VAE takes as input Z vector? It's the decoder. Okay, the cards were better than I thought. I thought I had put like encoder decoder, but I just put like one sentence encoder and another sentence decoder. That's good. Good design. Always synchronized because the counter is running. Anyway, so this is xt minus 1 sampled from p theta xt minus 1 xt minus 1 xt rather, or not even. Anyway, not that important. What is this? These are examples of conditional GANs usage. Fundamental limits of encoder is the fact that their lattice space is not structured and continuous. So 2 points, 2 close points can be very different, and it's not it's not even assured you can sample point anywhere in the time space because it's not structured. I hate this card. It's just this one with xt minus 1, whatever. Okay, what chain? Well, there's the forward chain and the reverse chain, the backward chain, if you wish, or reverse. Okay. So yes, forward to add noise and reverse to predict noise. The bit of the reverse chain is to transform noise into real image. The simple and tractable random distribution into the complex real images distribution. I expressed it differently. Discriminator judges if the generated image corresponds to the input signal. The transition kernel is this element with, okay. Yes, it's not parameterized because it's a reverse chain, so there is no diffusion rate parameter. Sketch to image, well, sketch and image. What can I say? The forward chain, the goal is to transform the complex real images distribution into the simple and tractable. So the last example, it was black and white. I think it's just like edges to real image. Outline, yes, the same, whatever. What GAN categories overperforms? I think it was the non-supervised GANs. Okay, I was really hesitating. It's the conditional ones. Yes, because you need to. Anyway. GANs are universal approximators of density. Because this variable is not observed, EM. Okay, so it's expectations steps where it outputs the probability assignments of the variable. Conditional distribution, yes, if you wish. That's a better word. 1 and around 1,000, 2,000. Intermediate step when you blur an image. Add noise, I mean. Examples, segmentation. I think it was black and white to color, or vice versa. Oh, wait. It was not this question. Yes, it was this question. One. Okay, one. Examples of models for non-supervised GAN. Conditionals, non-supervised. On my test, I would have written only non-supervised and omit the conditional, so I have to be precise. What GAN categories overperform? So it was the conditional ones, some types of conditionals, where you just put the image and ask for labels. We've seen it earlier. GMMs are universal approximators. I don't know if that's the correct word in English. What is that? These are the typical types of GANs you can encounter, categories of GANs, if you wish. Important elements to consider to train VAE, quality of the training data, properly pre-trained and so on. Generator takes as input noise and audio signal, and discriminator takes as input the image generated and the noise. The cycle GAN. That's the one from which we gave the 3-part loss formula. You learn to go in this domain, and you learn to go to the other domain, and you check the anyway, mesmerizing picture. Examples of models. Know that when you examples of models from conditional non-supervised. When you flip a card and check the answer, the counter is locked, so you can just spend the time you want and it will not count in the time spent. That's why the recorded times here often is lower than your typical chronometer, running chronometer. Well, I've also made a break where I forgot to turn off the chronometer, so it's even more different. Anyway, so color design is to transform the complex distribution P star in the simple tractable P distribution. That's the assignation douce. The kernel is Q of point x0. Expectation maximization is iterative algorithm used to parameterize probabilistic models using latent variables. I think that's the speech. To estimate parameters, to parameterize probabilistic model is perfect. That's the transition kernel. Each Gaussian of GMM is associated with weight. Downsides of GMM, so high computational cost. It's a relative process sensible to initial conditions, very sensible. Transformation is progressive because you add noise, and the noise. Conditional GANs are they supervised? Oh, good question. Are GANs conditional? Yes, because there is the opposite non-supervised GANs. But why are they supervised? Well, because you just smack them if I'm forgetting my fundamentals. What is a supervised AI model? Who did we ask yesterday? It was DeepSeek. What is a supervised AI model? Why can we say conditional GANs are supervised? I'm looking forward to the next DeepSeek drop, honestly. Oh, it's just that. Labeled data. Of course. Of course. I get it now, I get it. Okay, so match datas. Edge to image. Isn't it pix to pix? Yes, we've seen it already. Gives a simple schema of autoencoder. Okay, let's give it in the air. So you have your encoder that takes an image and outputs a prior. It's a vector in a Latin space. A Latin space is a vector space of a certain dimension. Often simpler than the real image space. And also it doesn't represent things in a sensible way. It's the own little space of the encoder. He uses it to represent what he wants. Anyway, then you have the decoder that takes this prior and generates the image back. And the loss, but the loss was not asked. The loss is simply difference between these two images, and there is a missing piece here. You often regularize with the difference between. Oh no, it's for the VAE. VAE, since you have a distribution here, you also compare the shape of the distribution to the shape of a normal distribution, and you penalize when the latent space, the probability distribution is differently shaped than a normal distribution. It's to enforce continuity in the distribution and stuff like this. Oh, whoa, it was perfect, man. Okay, anyway. Well, you just have like a head and movement and facial features, and you just output whatever you want, man. Not a boring question. It's a boring card because the card is like not even correctly done. You've seen it already. That's the complex distribution P star, which you take the initial image that you are going to add noise to. GMM, Gaussian mixture models. VAE, variational autoencoder, of course. Inconvenient of what algorithm for what models of EM for GMMs. Gives okay, we've seen it like 1,000 times. Okay, we get it. Oh, maybe we are going to finish this one. I was really hesitating to end the video and just go do something else. Maybe we can finish it. Initial generator, blah blah blah. Okay, we know this one. Is it the case for K-means? No, K-means, no. K-means, it's 1 point to 1 mean, not 1 point to this mean and this mean a little bit. What does it allow? To marginalize intermediate variables, to have a simpler loss function and gain some time. Oh Lord, haven't we seen like this 1,000 times? X1 is simply sampled from this. You added noise to the image and the kernel, and you sample from the kernel and blah blah blah. Each iteration augments the likelihood of the data. That's the principle. And that's the what stuff about it. Classic GANs, I think it was the typical GANs, same. What model? Plans to generate data, diffusion model. In GMM, what is the hidden variable? The hidden variable is the generating Gaussian of the data. Probabilistic models, also generative, that approximate GMM. Expectation optimization. Conditional non-supervised. So it was the weird initializing schema we seen. Let me just. Only 17. That's great. That's great. That's really efficient. Generator. So it takes as an input. What does it take? The generator takes a noise and outputs. No, sorry. Generators takes an image from domain X and outputs the same image in domain Y. Yes, sir. Yes, sir. Diffusion model 1000. GANs are overperforms. Generator outputs whatever. Encoder takes input an image. Advantage of EM for GMM. Discriminator judges what condition? If the labels correspond to the image or not. Sound to image, a noise and a sound. LVM, any generative model that uses latent variable, uses neural networks to parameterize its model and searches for probabilistic model like theta of x and z. These are two variables, and it's equal to the probability of z times probability of theta x given z. It kind of makes sense, but I'm not sure. Anyway, that's okay. So that's the x. That's this one. When you remove the last noise, you basically arrive to the complex distribution. You are generating something that could be from the complex distribution. GANs categories, there is the typicals, conditionals, and unsupervised conditional. So that's almost equal to the complex distribution. What is this? It's the typical GAN training loop. Conditionals, maximization of the likelihood, optimization of the parameters by increasing the weight and blah, blah, blah. Contraint, because it doesn't know the latent variable by definition. Okay, so qxt times 1, it's almost, it's approximately, this one is the adding noise, so it's almost the same as removing noise, predicting p theta of xt. It's the same. You remove the, oh sorry, I forgot we arrived. So here we are. Okay, it's the special case where it's like all noisy. I just didn't read correctly, but it's an easy one. non-supervised conditionals. What GAN category allows deepfakes conditionals? Of course, diffusion in complex P distribution. Oh, I'm so tired of these questions because they're like not important but hard to always summon to your brain. Not that bad actually. Quite good for the given materials. That is not that easy. And also the fact that I explained to you, because when I'm alone, I'm just like click, 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 click. It's a bit faster. It's a bit faster. So it's like around 12 seconds. So 3 seconds on average to explain and to a better time is cheaply paid. So what's the downside? Is it like damn, I don't know. I would have probably not guessed it. A DLGM is a type of DLVM. In a GMM, how is the resemblance of a point obtained? The likelihood of point in a GMM is obtained by summing the probability of each Gaussians. You ask each Gaussians, how sure are you that you produced this X? And they all say, oh, 0.22, 0.50. You add them, sum them, and it gives you the likelihood of X. I'm pretty sure. What? I think it's what I said, but I'm not sure. Anyway. Decoder takes as input Z vector and produces a distribution from which you can sample the final image. Parameter of the distribution is, of course, it's computationally heavy. Examples of applications. We had like black to white, night to day, sketch to real image, outline to real image, and picture from space, from the sky to a real map, like Google Map. Hidden variables. DLGM, sorry, yes, I read it like too fast. So that's great. That's actually a good thing we did tonight, to have learned this one. Then we'll learn this one, then we'll learn this one, and this will be done, and we can add little by little new elements. So like these ones, and these ones, and this one, this one, this one. And damn, that's a lot. And then we will go to be Mr. One, and then last year, and then license, and so on and so forth. Okay, so the last card, well, I'll do it, I don't know, sometimes in the evening. Well, that's all from me, at least for now. I don't know if I'll record something else. Anyway, kiss kiss.